Okay, in this video, we're going to take the curl of the position vector r. We're also going to take the divergence of the curl vector r, and we're also going to take the gradient of the magnitude of the position vector r. Also, before we go, we had 6 videos where we had proved different types of vector identities with the del operator. Also, before we had those identity videos, we've shown that for any vector, the divergence of the curl equals 0. And we had also shown that the curl of the gradient equals 0. Okay, now let's consider the position vector. And it is exactly what it is, the position vector. If I'm at a certain point in a vector field, it's going to have an x, y, and z point. So if I'm up here, then that's the position vector r. So it's going to have an x, y, and z, well, it's I, j, and k coordinates. And of course, this would be the value of it, of the quantity of the particular position vector. Now, what happens, say, if we take the gradient of the scalar quantity of the position vector, in other words, of this. So we want to know what is that going to equal. So we have the partial with respect to x, our gradient operator, like this. And that's going to operate on this. So what we're going to be doing is taking the partial derivative of this with respect to x, then do it again with respect to y, then do it with respect to z, and that will be the I, j, and k components of the resulting gradient vector. So taking the partial of this expression with respect to x, then we're going to have, bringing the 1/2 down, we'll have 1/2 times x squared plus y squared plus z squared to the minus 1/2. And take the derivative of what's inside, that will be 2 times x, and that is the I component of the resulting vector. Then we do the same thing, except now we're going to be taking the partial derivative of this expression with respect to y. So this would be plus, and again we're going to have 1/2 times x squared plus y squared plus z squared to the minus 1/2 power. And now we take the derivative inside with respect to y, and that will give us 2 times y, and that is the j component of the resulting gradient vector. And one more differentiation operation to perform, taking the partial of this with respect to z. So once again, we're going to have 1/2 times x squared plus y squared plus z squared to the minus 1/2. And taking the partial with respect to z, we're going to have 2z, and that is the k component of the resulting gradient vector. So we look, these will cancel. And we have x divided by, this is minus 1/2, so it would be divided by the square root quantity. Same thing with y divided by the square root quantity. Same thing with z divided by the square root quantity. So this is going to be equal to x times I plus y times j plus z times k divided by this, x squared plus y squared plus z squared to the 1/2. But this, that is our position vector r, as we stated right at the beginning. And this is the magnitude of it. So we have r divided by its magnitude. So that just gives us the unit position vector. So going back up to here, here's the position vector. This is its magnitude. You take the gradient of that, and the resulting vector that you get is the unit position vector. Okay, now let's move along and ask ourselves what happens if we take the divergence of this. So now we're going to consider del dot r. So again, here's our del operator. Like this. And we're going to take the dot product of this with the position vector, xi plus yj plus zk. So we take the dot product of these, and again, when we're performing this operation here of taking the dot product with the del operator, we're treating the del operator as an independent vector in its own right. So we do this, take the dot product of this, I dot I, that's 1. Now the partial of x with respect to x, that's from this component. Moving along, taking the dot product as we move along here, we'll have j dot j, that's 1. So we'll have plus partial of y with respect to y, plus k dot k, that's 1, under the partial of z with respect to z. And this, of course, is just 1. So we get that the divergence of the position vector equals 3. Okay, one more thing to consider here. What happens if we take the curl of the position vector? So now we have this. And again, using the matrix definition of the vector product, that's going to equal this expression. Like this. And to evaluate this quantity, we go ahead and we expand out the determinant. So we cover this column, we cover this row, and we're going to get the partial of z with respect to y minus the partial of y with respect to z, and that's the I component. And before we go ahead and expand out the rest of the determinants, let's look at what we have. Here, for the position vector, you're at some point in two-dimensional space, so you're going to have a certain x value, a certain y value, and a certain z value for our position vector. And we have this expression here, the partial of z with respect to y. Well, there is no partial of z with respect to y. So this is 0. Likewise, the partial of y with respect to z, there is no change in y with respect to z. So that's 0. Let's look at the other components here. To get the j component, we cover this column up and this row up, and we work with this 2 by 2 matrix, and we have, and that will be minus the partial of z with respect to x minus the partial of x with respect to z for our j component, and z does not change with respect to x, nor does x change with respect to z. So that's 0. And for the k component, of course, we cover up this column and this row, and we work with this 2 by 2 matrix, and that gives us, taking the determinant of that 2 by 2, with the partial of y with respect to x minus the partial of x with respect to y for our k component, for both of these are 0. So the curl of the position vector is 0. So these are the three basic properties of the position vector that we wanted to establish in this video. And again, remind you now that for all vectors, the divergence of the curl is 0, and also, this is an x sign, not a plus sign, the curl of the gradient is also 0 for any vector. Okay, that's it for this video. Come back and join us in the next video, and we're going to consider some more properties yet of the del operator. And also, to remind you, there's hundreds of problem-solving videos at the website, digitaluniversity.org. If there's any particular aspects of these subject matter you think need to be clarified, or that you would like to see perhaps some more solved problem examples, let us know with your responses and comments, and we'll see what we can put together. That's it for now. Come back and join us in the next video.